So since we have a lot of material to cover, I'll get started. Okay, so if you remember, we were discussing this rather complicated relational algebra example of products, purchases, companies, and persons. And we had this complicated looking tree that we came up with at the end of it. So that's going to be all of it, all of what we're going to cover about relational algebra. So I don't know if I covered this in the previous class, but it's fairly hard to get good at relational algebra unless and until you do a lot of examples and a lot of practice problems. So go ahead and do those. Find sort of questions on in the textbook. Find questions in other textbooks, and try them out. Okay, so that's the only way you're going to get good at it. You need to develop an intuitive understanding for how to assemble these pieces and how they work together. And the best way of doing that is through practice. So I encourage you to do that. If you have any questions, feel free to post them on Piazza, even those that are not part of the homework. If they are from the textbook or from other sources, you're more than welcome to post them on Piazza, and we'll try to help out. Okay? So one last little topic before we get into schema design or schema, sort of relational schema management. That is the issue of sets versus bags. Okay, so far we've been talking about sets of tuples. A relation consists of a set of tuples, and our relational algebra is also based on a set-oriented notion. Remember, we had the union, intersection, difference operators. All of these were set-oriented operators as opposed to something else. Okay, so as it turns out, there's an equivalent bag-oriented relational algebra, which is not set-oriented; it's bag-oriented. And what a bag means is sort of kind of intuitive. It is basically you don't enforce the standard property for a set, which is that things are unique, right? So in a set, there's only one copy of each item. In a bag, there can be multiple copies of each item. So this is the same as what is known as multi-sets that you might have encountered in other classes. Okay, so there's a equivalent bag-oriented relational algebra. And as it turns out, actual relational databases use bags as opposed to sets. And the reason for this is because these operations are actually more efficient than the corresponding set-oriented ones. Okay, so even though I've been telling you a lot about sets, that's not what most industrial strength databases do. They actually use bags as opposed to sets. Okay, so now that we know the notions corresponding to sets, how do these notions translate to bags? Okay, so if, for instance, you're trying to perform a selection operation on a bag, then what it's going to do is to preserve the number of occurrences. Okay, so for instance, if you had AB and then A1X, A1Y, A2X, A2Y, and I had a selection operation which is select A is equal to A1, then actually, let me keep 2 copies of this guy. Okay, so I have 2 copies of A1 is equal to X, A1 X, and then A2X, A2Y. If I select A is equal to A1, I will get rid of these 2, but I will retain both of these copies, so it will preserve the number of occurrences. Okay, so nothing too surprising. And the speed for this operation is roughly the same as the speed for sets. So there's no real benefit to performing selections using the bag relational algebra as opposed to a set relational algebra. However, the projection is actually much faster. So if I'm trying to do a projection, so once again, let me try to use my same example. So I have AB, A1X, A1X, A2X, A2Y, right? And I wanted to project on B. Okay, so project on B this relation R. Okay, so what I would have to do in the set case is to basically get rid of the A values and then take this set of values and then collapse it down to give me X and Y, right? Because it has to look like a set, right? It can't be a bag. On the bag algebra, I don't need to do any of that. I just need to eliminate all of the values corresponding to the attribute A, and then I can preserve the number of instances corresponding to B. Okay, so it's much easier because I don't need to do duplicate elimination. What's one way of doing duplicate elimination? One way of doing duplicate elimination is to sort the entire set of values, then go down that list and preserve one copy of each thing. Right? That's expensive. Most ways of doing duplicate elimination are going to be expensive. So instead, in this case, in the bag relational algebra case, you preserve the number of occurrences, and therefore the projection operation is actually much faster than in the standard set-oriented relational algebra case. Any questions about that? Okay, so Cartesian products, joins are actually also straightforward. So basically, every copy joins with every copy. So if you have two relations R and S, and you have a tuple corresponding to X, two tuples corresponding to X and two tuples corresponding to Y. Y is just my way of, X and Y are just my way of denoting those tuples. You will have basically all combinations of these things, right? So you'll have 4 tuples that arise as a result of the Cartesian product or the cross product. Okay, so you basically preserve the copies, and every copy joins, or every copy would cross product with every other copy. So this is going to be faster than sets because once again there is no duplicate elimination. Okay, so then the set-oriented notions. So in the set-oriented notions, this is where we have to be a little careful. The projection, selection, and cross products are fairly straightforward. The set-oriented operations are a little more tricky. For the union operation, if I'm trying to do a union of 2 sets, what I'm going to end up doing is to add the number of occurrences in the 2 sets. Okay, so you have one occurrence of A here, one here, so you have 2 copies of A here. You have 2 copies of B here, 3 here, so you have 5 copies of B here, and so on. Okay, so the union on a bag, in the bag algebra case, is basically you add the number of occurrences. So in this case, once again, this is faster than sets because you don't need to look for duplicates, right? So you don't need to check that, hey, this is a duplicate of this, and therefore I need to retain only one copy of it. Yes?
Does it have to be like in a sequential order, as in like all the A's are grouped together?
No. So in both sets and bags, the order does not matter. It's just that the bag algebra case can have multiple copies of the same thing. The order does not matter. So these are sets. I mean, these are multi-sets. Okay? Any other questions? The only reason I wrote these out in order is because it's easy for me to compare them, but it's not necessary. Okay? All right. So the difference operator. So yeah. So one last point about the union. This is faster than the set-related or set-oriented union because I don't need to look for duplicates. So the difference operator is similar to the union operator. Here you subtract the number of occurrences, right? So here you have one occurrence of A, no occurrence of A in this set. Therefore, you have one copy of A. You have 3 copies of B, one copy of B here. So you have 2 copies of B left. 2 copies of C here, 3 copies of C here. So therefore, you can't store -1 of something. So you're going to end up removing all the C's. So this is your final result. Okay, and this is a similar speed actually it is in both cases you might need to identify the number of copies and take that into account, both the bag algebra and the set-oriented relational algebra case, and therefore this is a similar speed for both sets and bags. Similarly, the intersection case, here you would retain the minimum number of occurrences across the 2 groups of things that you're trying to intersect. Once again, this is a similar speed compared to the set-oriented relational algebra case. Okay? So here in this case you had 3 copies of B, here you had 2 copies, therefore you retain 2 copies, right? So here you had 2 of C, 4 of C, therefore you retain 2 of C, and the others don't get added because there's no copy in the corresponding other set. Right? So overall, most operations are either faster, like the projection, the cross product and joins, the union, all of these are faster. The other operations are roughly the same speed. So that's why production database systems, industrial database systems, open source database systems typically use bag relational algebra as opposed to set relational algebra. This is just for speed and performance. Okay? Otherwise, it often always makes sense to use the set relational algebra. That's what we would like, but a bag relational algebra is a compromise. Okay? So that's it with relational algebra. Any questions about this? Any questions about the material we covered last time? Any questions about bag algebra? All good? Okay. Feel like I may have uploaded the wrong thing. Give me a second to check. Yes, I most certainly did. It's going to take me a couple of minutes to fix. Huh. Apparently I do have this file here, so I don't know what I did. Okay, let me try to edit that. Okay, I did upload it. I just linked it to the wrong thing. Okay, cool. Where do I save? Let's get it auto-saved. Okay, this seems to be a different. You guys see any box that indicates save? No, right? Okay, let's see if it auto saves. Nope. All right. Sorry for the delay. All right. So this is our next topic, relational schema design. So before that, I wanted to mention a few announcements. Homework 1 is due today. Stage 1 of project is due today. Homework 2 will be out today. So watch out for that maybe in the afternoon or so. One thing that I wanted to mention is that we aren't seeing as much activity on Piazza from you folks on answering others' questions. So remember that there's a substantial bonus for this. Last year it made the difference between whatever, an A minus and an A for many, many students. So there was a grade boost based on this Piazza activity. So this is something I encourage you to do because we aren't seeing as much, and it's sort of an easy way to get points because you help out your student, help out your fellow students, and you learn something in the bargain. Okay, so that's something I wanted to mention. All right, now back to schema design. So first question is, how does this fit into what we've learned so far? So we talked about the notion of ER diagrams. This is a way of conceptualizing or formalizing our requirements into a pictorial form, right? And then we talked about how we can translate these ER diagrams into a relational schema, something that can be represented in a database. We talked about data manipulation using relational algebra, which is a formal language that allows us to query the data in these relations. So in some sense, now we know how to construct relations and the basics of querying them. Unfortunately, the data definition story is not quite complete. So before we complete the data definition story, it turns out that it's not sufficient to simply map the ER diagram or ER model into the relational schema and be done with it. There's a little bit more work to do. This is because the ER diagrams that you may end up with may not be satisfactory. Sorry, the relational schemas that you may end up with may not be satisfactory. Okay, so let me try to illustrate. So like I said, we've designed an ER diagram, translated into a relational database schema, which is a set of relations R1, R2. We can do the following. We can implement R via a SQL query and start using it. However, this schema may not be well designed, and this may cause a lot of problems in the bargain. Another reason why we need the topic that we're going to be talking about today is that people may start without an ER diagram. Okay, if people start without an ER diagram, they already have a relational schema. How do you improve it? How do you get to the point where it sort of has desired properties? Okay, this is often the case. People just do something without thinking about it, and then you have to fix the mistakes later. Okay, so for two reasons. Why? First is the schema that you might get after ER diagram translation, it may not be well designed. And the second case is because people may start without an ER diagram, and therefore you need to reformat it. Okay, so either way you need to improve the schema. So let me start with an example. Okay, so let's say you had a single relation corresponding to a person. You had three attributes, SSN, phone number, and address, and you've translated that into the following relational schema. Right, so this is the standard way. You had one entity set, you translated it into a relation. So what are the issues with this schema? Right, so the first thing to notice is that you have an SSN identifier, but a single SSN could have multiple phone numbers, but at the same time has a single address. Okay, so a person lives at a given place, but could have multiple phone numbers. Okay, so what are the issues with this schema? Any thoughts or guesses? Yep.
You have just one attribute which is different, and two are just being repeated.
Right. So the issue here is that you are repeating both of these attributes for all of the tuples corresponding to one for each phone number. Right. So implicitly, you do need the SSN. Because that's an identifier for the person, but this address field is being repeated, right? So this is one issue. What are other issues? All of these issues stem from the redundancy, in fact.
So if you want to query the phone number of a specific SSN
So his point was, if you want to query the phone number for a specific SSN, it might give you two numbers. That's not quite a problem because that's what we want to encode. If a person does have two phone numbers, we can't really prevent that from being stored in the database, right? We do want to store that. Yep.
If we want to update the address of the SSN, we need to do it twice.
Correct. So if you want to update the address for a given SSN, we need to do it twice. So let's say this SSN, this person moved apartments and moved from 10 Green Street to 5 University, then you need to update that in all copies of this person's record, right? You need to do it twice in this case. The second issue stemming from this update is that you may, by mistake, update it in one place but might forget to update it in the other place, and that could lead to an anomaly. Okay, so the last issue is that you may, when doing deletions, you need to be careful. Okay, so let's say you have to, you said, this person, this SSN, said, you know what, my phone number, this phone number is no longer active. Please go ahead and delete that from the database. So in this case, I have to think about two things. The first is, if there is another record corresponding to that person, then I can go ahead and happily delete this tuple. But if there is no other record corresponding to that person, if that person does not have another phone number, then by deleting that tuple, okay, what did I want to do? Okay. So let's say you've already gone and deleted this, and this person said, hey, go ahead and delete this phone number as well. By deleting this phone number, you get rid of their address information as well. Right? So because of that, you may need to reason differently based on whether you have multiple phone numbers or whether you have just one phone number. If you have multiple phone numbers, you can probably go ahead and delete the tuple. If you have a single phone number, maybe you want to mark that phone number as null, right? And then keep the address around, because otherwise you lose the address as well. Does that make sense? Okay, so there are three issues here. The first is the issue of redundancy, right? The second is the issue of update anomalies, and the third is the issue of deletion anomalies. Okay, so the issue with redundancy is that you're storing the same information twice. The issue with update anomalies is that if you update the address of in one of the tuples, you have to update the corresponding address in all of the other tuples that correspond to the same individual. And if not, there could be two addresses for a given person. You don't want that. And then finally, you have deletion anomalies. So deleting the phone number of a person, if you're not careful, the address can also disappear along with it, right? So you need to figure out whether there is one copy of the phone number or multiple copies. If there's one copy, then you may want to mark that as null. There are multiple copies, you can probably go ahead and delete the corresponding tuple. Okay, so these are the issues with this schema. So how do we improve it? So the way to improve it is to actually break this up into two relations. So the first relation corresponds to a SSN and address, and the second relation corresponds to SSN and phone number. So first question is, how do I get these two relations from the original relation SSN, address, phone number? How do I get these two relations? This should be straightforward. Using relational algebra, you do a project, right? It's as simple as that. So you do a project starting from this relation down to SSN and address in this case, and SSN and phone number in this case. Yes?
Because we assume SSN is unique, so like in a general case, we always project using an attribute and also, well, not an attribute, but one set in a sense, and like a unique.
So, so the question is, do we usually project based on some identifier that allows you to identify the entities in the relation, so in some sense a key. Not necessarily. So let's say I want to find all the addresses that people live at. I might not care about projecting on SSN, right? So it depends on what I want. In this particular case, yes, I am doing that. Yeah. But not in general. In general, I can use the projection for anything, right? I can say...
but like if you want to break a relation into two,
Yeah.
then you have to
Yes, yes, yes. That's a good intuition. Remember that. So you're saying if I wanted to break a relation in two such that I can associate items across these relations, then I need a way to capture that information in some way. This identifier or key allows me to do that. That's a good intuition. We'll revisit that later in the topic. Okay. So these are nothing but projections. Okay, so far. Unfortunately, these sorts of anomalies are not something you're going to detect even if you did principled ER diagram design and translation. The fact that this design is better. Why is this better? Well, you're storing each address precisely once, right? So you won't have the issue of redundancy. You don't have the issue of update anomaly because you will end up editing precisely one thing. You don't have the issue of deletion anomaly, right? Because if you delete a phone number of a person, the address is not getting deleted as well. So these three issues, redundancy, update anomaly, deletion anomaly, don't carry over to this schema design. Okay, so they were present in the earlier schema design. They don't occur in this one. Okay, so how do we go about obtaining a good design? Typically, the process starts as follows. You start with the original database schema R. This can be via ER diagram translation or otherwise. And then we repeatedly transform it until you get a good design R star. Okay? And the goal is to end up with some desirable properties for R star at the end of it. Right? In our previous case, we saw that the R star that we ended up with has no redundancy, no updation anomaly, no deletion anomaly, and so on. Right? In this case, there are other desirable properties in general. You want to preserve the amount of information of R. You want to have the minimum amount of redundancy. You want it to be dependency preserving, and we'll get to this notion later. And you want it to have good query performance. Usually, though, these properties are very hard to satisfy all at the same time. So we might end up making some compromises. Okay, so it's still fairly challenging, even though you want all of these properties to be satisfied. Yes?
What do you mean by good query performance?
So when you're breaking up the relation into two, like we saw in the previous case, if you wanted to query the combined information, SSN, address, phone number, then implicitly, if you've broken it up into two relations, you will have to do a join, right? And joins are going to be more expensive than simply reading the contents of a relation. So while that previous approach was nice in terms of minimizing the amount of redundancy, it has poor query performance. Okay? Poorer query performance. But that's usually a trade-off we are willing to make because redundancy is a more it's a harder issue to deal with than query performance. Query performance you can improve in other ways.
But doesn't that depend on the kind of data you have?
Doesn't it depend on the kind of data you have? Not necessarily. In this particular case, okay, so it depends on the number of the kind of data that you have, and it depends on the kinds of queries that you have. If your queries are typically touching SSN and address and not touching the phone number, breaking it up is a great idea, right? If your data is often such that, I don't know, in most cases doing a join is more expensive, but the data itself might have so much redundancy in the first case that the join might be cheaper than looking at the original data, right? So it's hard to tell, you're right. I mean, it depends on the data, it depends on the kinds of queries. Often these questions are fairly hard to answer, but we typically opt for removing the redundancy because that could lead to performance problems are a smaller issue, you can always deal with that, but Anomalies are a much harder issue to deal with, and if you have redundancy, you lead to anomalies. Those are a much more problematic case to deal with within your database. Anyway, so I'm still at a high level right now. All that I'm saying is there are lots of properties that you want these schemas to satisfy. It's hard to satisfy all of them at the same time. So we try to figure out how to trade off these aspects. So how do we go about obtaining a good design? So as it turns out, there's been a lot of work on developing what are called as normal forms. These are sort of canonical ways of doing schema design. These have been developed over the course of many, many decades now. And a normal form is basically a schema that obeys certain canonical rules. Converting a schema which does not obey these rules into one that does obey these rules is what is called as the process of normalization. This normalization process typically involves breaking up a table into one or more tables, like we saw earlier. Okay? And the opposite of grouping tables together to give larger tables is the notion of denormalization. Okay? And often we don't do denormalization unless our queries are very, very specific and the performance requirements dramatically require that you do denormalization. But often we go in the other way. So we start with a big relation, we break it down into smaller relations. So we often do normalization rather than denormalization. And so there are many different normal forms. You're going to be covering a couple of them in class. And if R star, the eventual schema that we end up with, is in one of these normal forms, then it's guaranteed to achieve or provide certain good properties. Okay? So for instance, if R star is in Boy-Scott normal form, which is also known as BCNF, then it's guaranteed to not have certain types of redundancies. Okay, so there are lots of algorithms to convert R into R star in these normal forms. We'll cover all of that in a little bit. Like I said, there are trade-offs between these normal forms. Some of them opt for performance, some of them opt for redundancy, some of them opt for what is called as dependency preserving properties. We will get into that later, but our overall goal is to learn these forms and try to figure out how to convert from one to the other, or rather from the original relation to one of these normal forms, and also understand the trade-offs between them. But before that, we need to understand the notions of functional dependencies and keys. So that's going to be the topic of the rest of this class. Okay, so functional dependencies. Functional dependencies are a form of constraint, and therefore they are part of the schema. Okay? And finding these functional dependencies are part of the database design. Okay, so this is something that you do when you're designing your database. And these functional dependencies are heavily used in changing the schema of your database. So this is used heavily in normalization. Okay. One important thing about functional dependencies is that they hold for all instances of the database. So no matter what data is present in the database, they continue to hold. All right. So the definition of a functional dependency is that if two tuples agree on a set of attributes A1 through AN, then they must also agree on the attributes B1 through BM. This is denoted using the following notation. So A1 through AN on the left hand side with this arrow and B1 through BM on the right hand side. Okay? So you would read this as A1 through AN implies B1 through BN, for instance. Okay? Or B1 through BN is dependent on A1 through AN. Okay? So what this says is that if two tuples share the same values for A1 through AN, then they share the same values for B1 through BN. Okay, so where have we seen this before? So we've seen this before during ER diagrams and conversion using SQL to a relational model. Where have we seen this? Where have we seen the notion of if two tuples share this set of values, then they also share the other set of values? Keys, right? So keys are an example of a functional dependency because if you have two attributes that have the same values for the keys, then they have the same values for the remaining attributes, right? So implicitly, key implies rest of attributes is a functional dependency. That makes sense? So any two tuples that share the same value for a key also share the same values for the rest of the attributes. So key implying rest of the attributes is also a functional dependency. But functional dependencies are a lot more powerful. It's not just restricted to keys. It's much more general than that. Is this clear? Yes? Okay. All right. So looking at this example, we could potentially infer or confirm that certain keys are valid. So let's say I wanted to check whether this, not key, but certain functional dependencies or FDs for short are valid. So let's say I wanted to check whether this is valid. Emp ID implies name, position, and phone. So the first thing to notice is that the emp ID is unique. If it is unique, then obviously it's trivially true, right, that this property holds. There are no two tuples that have the same value for emp ID, and because of that, I don't really need to check this property at all. So if I wanted to verify whether this functional dependency holds on this database instance, that's easy to check because all of the emp IDs are unique, right? Because emp IDs are unique, there's no two tuples that have the same value for emp ID. So trivially, the tuples that are present in this relation satisfy this functional dependency. Yes? Okay. Does position imply phone? So let's take a look at that. So clerk has a value 1, 2, 3, 4. Sales rep, there are two tuples corresponding to sales rep with value 9, 8, 7, 6, and one corresponding to lawyer. So the only thing that I need to verify is that these two tuples, which have the same value for sales rep, have the same value for phone, or same value for position, which is sales rep, have the same value for phone, and that is certainly true. And because of that, I can verify that this functional dependency holds on this instance, right? So this functional dependency holds on this instance because if you consider all the tuples corresponding to clerk, yes, it holds. If you consider all the tuples corresponding to sales rep, well, there are two of them, and both of them have the same value of phone number, so it holds. Consider all the tuples corresponding to lawyer. Once again, there's a single value corresponding to phone, so it holds, so we are good. Okay? So on the other hand, if I wanted to verify whether phone implies position, this is not true. Why? Yes?
Because if you look at clerk and lawyer, they have the same phone number.
Correct. If you look at clerk and lawyer, they have the same phone number, right? So you have two tuples that have the same value on the left-hand side of this functional dependency, which is phone, but don't have the same value on the right-hand side, so clerk and lawyer, right? So these two tuples violate this functional dependency. All right? Okay. So let's go back to what a functional dependency actually means. So we talked about the formal definition of A implying B, which is if two tuples satisfy have the same values for A, then they have the same values for B. but this is more general than that. A functional dependency is more general than that. The functional dependency, if you say that A implies D, if you know that this is true in relation R A B C, then for all valid instances, okay, so for all instances that will exist in the real world, A will determine or A will imply B. Okay? So if two tuples share A, they will share the same B. Okay, so this is a property of the world. So if you say that SSN implies name, this is a property of the world. This will hold true no matter whether new individuals are born or die. It's going to hold true independent of all of that. Okay, so this is a property that holds true in the data, and therefore this is something that I need to respect no matter what the instance is. So it's not an instance specific property, it is a global property. This holds no matter what the instance is. Right? On the other hand, if A does not imply B, there is no guarantee that the A determines property holds in a given instance. Okay, so what that means is that if A does not determine B, then you don't know whether for a given instance whether A determines B or not. Okay, so like I said, this is a property of the world rather than a specific instance. So if, let's say, a relation has a single tuple, okay, so if a relation has a single tuple, so you have R with A1, B1, C1, then you may be tempted to say, you know what, I can come up with any functional dependency and it holds, right? I can say, hey, A implies BC, C implies AB, and all of these functional dependencies hold. You can do that because you can look at this and say, look, there is only one tuple, and therefore trivially any functional dependency would hold, right? Except that that's not the case. The thing to remember is that when a functional dependency holds, it holds for all instances of a relation, right? Even though in this specific instance maybe other functional dependencies may hold, they may not hold in other instances, and therefore you can't conclusively look at a relation instance and say, hey, these functional dependencies hold. Okay, so the thing to remember is you can't look at a relational instance and say, yes, these functional dependencies hold or not, because you have to look at all instances and see whether the functional dependency holds. What you can confirm is whether a functional dependency does not hold. If you see a relation instance where a functional dependency does not hold, then you have a counterexample, right? If you have a counterexample, you know for sure that that functional dependency does not hold. Does that make sense? Any questions? Okay, so basically A implies B means that for all valid instances A will imply B. If A does not imply B, then we don't really know whether it will hold true for a given instance or not, but what we know is that it doesn't hold true in general. Okay, so here's an example. All right, so in this case I have a product relation where, for instance, maybe name and manufacturer implies the price. The person relation may have SSN implies the name and the age. A company relation where the company name implies the stock price and the president of the company, right? So these are other examples of functional dependencies, right? So let's try to test our understanding by looking at this relation. So let's say you have this relation which has SSN and phone number, and I have in this particular case all of these phone numbers are distinct. So the question is, can I look at this relation and tell whether phone number implies SSN or not? And the answer is no, because I don't know whether it holds true in general, right? This relation, in this particular relation, yes, I have distinct phone numbers, therefore there's no tuple that violates this functional dependency. But remember that a functional dependency is a global property that holds true of all instances. Therefore, I can't look at a specific instance and tell whether this functional dependency is true or not, right? So like we discussed, this is a property of the world, not of the current data instance. In general, you cannot conclude from a given instance of a table that a functional dependency is true. A functional dependency is not an observation made from the table's current tuples. Okay, it's an assertion that always has to hold true no matter what the database instance. Okay. On the other hand, I can check if a functional dependency is violated using the current using a relational instance, right? So if I want to check if SSN implies phone number, I have a counterexample to that, right? So these two tuples say that SSN does not imply phone number, so I know that for a fact SSN does not imply phone number using this instance. Okay, so I can tell that this functional dependency is violated by the current instance. I can't tell for sure if a certain functional dependency holds on across all instances. Okay, so going back to our example of key as a functional dependency, a key of a relation is a set of attributes that functionally determines all attributes of R, and none of its subsets determine all of the attributes of R. Right? So this is a more formal notion of the notion of keys that we saw even in ER design. So a key of a relation is a set of attributes that functionally determines everything else, and none of its subsets functionally determine all of the other attributes. Determine or imply are the same thing, so it's just a way of describing the functional dependency. So if you have a relation like this with student, UIN, email, department, and age, there could be many different keys for this relation. One key is the UIN, because the UIN determines UIN, email, department, and age. And also the email, right? Email is also a key because the email determines the UIN, email, department, and age. Right? So both UIN and email are keys, two different keys for the same relation. Any questions? Okay. So then there's the notion of a super key, which is another concept that we need to know. A super key is nothing but a superset of a key. So it's a set of attributes that contains a key. So given this this relation, what is an example of a super key? Yep. UIN and email, sure. UIN and email is an example of a super key, but there are other examples as well. Yes?
We can combine UIN or email with any of the other attributes.
Correct. So it's basically UIN or email plus pretty much any of the other guys, right? Department and age. That is also a super key. Right, so UIN, department, age is a super key. UIN by itself is a super key. Email, age is a super key, and so on. Okay, so all of these are super keys because they contain a key, right? So they contain a key, and therefore they are a super key. So another way to think about a super key is these are all sets of attributes that if you place on the left-hand side of a functional dependency, you can place all of the attributes of the relation on the right-hand side, and that functional dependency would hold. Okay? Make sense? All right. So let's walk through how one may think about sort of enumerating the functional dependencies that hold in a given relation. So let's say I have a relation which is called movie info with name, year, actor, director, and studio. And I have the constraint that the same movie can be remade multiple years, but a name-year pair uniquely determines a movie. So I'm saying that a name-year pair is a key for a movie. Okay, so let's say I have the first constraint, which is that a movie has a single director or studio, but may have many different actors. So what then? If a name year uniquely determines a movie, that does not mean that it's a key for this relation. So I'm sorry about that, because there could be multiple actors for the same movie. Okay, so that's something that we need to be careful about. All right. So the first constraint is a movie has single director or studio but has many actors. The way to encode that is that name, comma, year implies director, comma, studio. So that's one functional dependency that holds. Also, another functional dependency that holds is name, year implies director, right? It's simply a subset of the right-hand side here, so therefore it's trivially true. And name, year implies studio, okay? Just to read through what each of these things mean, if two tuples have the same values for name and year, then they have the same value for director and studio. So that's true, because a movie has a single director and studio. If two tuples have the same value for name and year, then they have the same value for director. That's true, because the movie has a single director. If two tuples have the same value for name and year, then they have the same studio. Again, that holds true, because a movie has a single studio. On the other hand, name, year does not imply actor, because there could be multiple actors in the same movie. So name, year does not imply or does not determine actor. Okay, so that's our first constraint. Then our next constraint is a director works only with a single studio. The way to encode that is director implies or director determines studio. Right? So a director works with only one studio, therefore director implies or determines studio. So an actor works on a given movie only once. So an actor never works on remakes of a given movie, but may work for many movies in a year. So how do we encode that as a functional dependency? So the actor, comma, name implies the year. Basically, if you have two tuples which have the same value for actor and name, so actor and movie name, then there is a single year at which that actor acted in that movie. So for instance, if an actor acted in King Kong in a certain year, they're not going to act in King Kong in a remake of King Kong. Okay? So actor year implies, actor name implies year is a way of encoding the fact that an actor works on a given movie only once, never for remakes. But at the same time, an actor may work for many movies in a given year. What that means is actor, comma, year does not determine the name of the movie, right? If you have two tuples corresponding to actor, comma, year, they don't need to be associated with a single movie. There could be two different movies the actor acted in that year, and therefore this functional dependency, actor year implies name, does not hold, right? It does not hold. Okay, so this is how you would take the requirements from the application and then may translate it down into a set of functional dependencies that hold in that application. So starting from these functional dependencies that we wrote down, are there any missing functional dependencies that we didn't capture given these requirements? So while it's certainly true that we've captured all of the requirements as functional dependencies, that it doesn't hold true that we've captured all of the functional dependencies that hold in this relation. Right? Can you give me an example of a functional dependency that I've not listed but that holds? Yep.
Name studio director. Like
Name studio implies director. So,
I mean, it might be multiple years.
yeah, so given the requirements that we have so far, there's no way of us being able to tell whether that holds true or not. So we have to assume that it doesn't hold true. What I wanted to ask is, what are sort of obvious ones that we missed?
The actor will determine the name.
Actor would determine the name, so that the name is the movie name, right? So an actor may act in many different movies. Therefore, actor does not determine movie name. Yep.
Name director determines the year. Like assume director only directed a movie. A director do not direct movies with the same names.
A director did not direct 2 movies with the same name. So again, you're adding additional information. I think that might actually be correct or true in the real world, but we don't know right now, right? So given this information, I can't add any new information. So all I was asking for was more obvious functional dependencies that hold given this setting. And there are lots of them, okay? So maybe this was a bit of a trick question. So what are the other functional dependencies that hold? So let's say I took director implies studio, okay? So all that I know is director implies studio, okay? Now,
Name year to studio.
Name year to studio, I already have that. Okay, so before I get there, so let's say I have director implies studio. You can see that I can add pretty much any attribute on the left hand side and the functional dependency will still hold. Right? So I can have, for instance, I could have actor, comma, director implies studio. Why is that? The reason for that is that if 2 tuples share the same values for actor and director, then they certainly share the same values for director, and because of that, they have to share the same values for studio. So I can pretty much add anything to the left-hand side of this functional dependency and it still holds. Right? Okay. Another thing, right? So let's say I have director implies studio. What if I decided to add x here for some attribute x, and then I decided to add x here for the same attribute x? Once again, this holds, because if 2 tuples have the same value for director and this attribute x, then because of director they have the same value for studio, and because they have the same value for x, they obviously have the same value for x, right? So basically, starting from these functional dependencies, I can create an arbitrary number of functional dependencies by simply adding stuff to the left hand side, or adding the same thing to the left hand side and the right hand side, and a bunch of other rules that will help me generate other functional dependencies, okay? And we'll cover that next. But at least is the intuition clear? Are we all clear on the notion of functional dependencies and the fact that yes, you can codify the requirements as functional dependencies, but there are a lot of functional dependencies that are effectively implied given the set of functional dependencies that we have. Does that make sense? Yes?
In the second one, you're just implying something like x is x.
Yeah.
It doesn't make sense.
Does it make sense?
That would always be there.
That will always be there. Yes, it's a trivial change, right? It is a trivial change, but it holds. So all that I was asking was that is this a functional dependency? Yes, it is a functional dependency. So the question is, are we missing any functional dependencies? Yes, we are missing, because if you wanted to enumerate all of the functional dependencies that hold, then we are missing this. But you're right, it's a trivial functional dependency and not very interesting. I would much prefer to have director implies studio than x comma director implies studio comma x. Right? You're right. But it's a trivial functional dependency, but it's a functional dependency that holds. And as it turns out, these trivial functional dependencies actually help you get to more complicated functional dependencies that would surprise you. So it's important to know how to get to these trivial functional dependencies as well. Okay? So with that, let me get into the next part. Okay, so all right. So so I had this actor name year implies director studio. How did I get that? Intuitively, I have name and year implied director and studio, right? And I added something on the left hand side, and therefore that is still a functional dependency, so that holds. How did I get director actor name implies studio comma year? Well, actor name implies year, director implies studio, and implicitly that allows me to get to this functional dependency, right? So if I have two tuples that have the same value for actor and name, then they have the same value for year. There are two tuples that have the same value for director, and they have the same value for studio. Therefore, this functional dependency holds. Okay? Okay, so let's systematize this, right? So we have some intuitive idea of how to construct these new functional dependencies. How do we systematically discuss these? Okay. So let's start with simple rules. So the simplest rule is basically you have A1 through AN on the left hand side, B1 through BM on the right hand side. This is equivalent to A1 through AN implies B1, A1 through AN implies B2, and so on up until BM, and we can replace one of these for the other. So if you have this set, I can replace that with this, and I can replace this guy with this set. Okay, this is trivially true, right? This is basically if A1 through AN have the same set of values, then B1 through BM have the same set of values, and therefore each one of B1, B2, B3, and so on up to BM have the same set of values. Okay, so you can replace one of these for the other. This is a simple splitting slash combining rule. Here's another trivial functional dependency. So if you have A1 through AN, then you can imply A1 from that. Okay, so in general, if you have A1 through AN, implying B1 through BM, and if B1 through BM is a subset of A1 through AN, then it holds, right? So if you have name comma UIN, this certainly implies UIN. Why is that? Well, if you have two tuples which have the same value for name and UIN, they obviously have the same value for UIN, and therefore this makes sense. Okay? This is an example of a trivial functional dependency. Any questions about this? Okay. So let's talk about the notion of a closure of a set of attributes. Okay, so given a set of attributes A1 through AN and a set of functional dependencies S, and I want to find all the attributes B such that for all of the relations that satisfy S, they also satisfy A1 through AN implies B. So I want to find each of those attributes, and the way to denote this is as A1 AN with a plus sign on top. So this is a closure of a set of attributes. So the closure is a set of all such attributes, and we will discuss why we need attribute closures in a little bit. So how do we go about computing the closure of a set of attributes? So the way to compute the closure of a set of attributes is to first split the functional dependencies in S such that every functional dependency has a single attribute on the right hand side. So you simplify the functional dependencies, the first step. And then you start with A1 through AN. And then you repeat until this set X does not change. You repeat the following. You repeat if B1 through Bm implies C is in this set S, so set of functional dependencies S, such that B1 through Bm is in X and C is not in X, then you add C to X. Okay? So if B1 through Bm implies C in it is in the set of functional dependencies such that the left hand side, this side is part of X and C is not part of X, then you add C to X. Okay, and then you repeat. That's it. It's very straightforward. The only first step is you simplify the functional dependencies before you start applying closure. And then you keep doing this up until you can't change the set of attributes X any longer. Okay? So the first question is why does this algorithm converge? Any sense for why this converges? Why doesn't it just keep iterating indefinitely? Any guesses? So one way to think about this algorithm is at every step you're finding a functional dependency such that its left hand side is in the set of things that you've found so far, but the right hand side is not, and then you add it and then you keep going, right? So in each iteration you are increasing the set of attributes in X by 1. Since you're increasing the set of attributes in X by 1, there's a bound to how many attributes X can contain, right? How many attributes can X contain? This is an easy one. Yep. What is M? Okay, so how many attributes can X contain? N plus M? Well, it's a simpler answer than that. As you keep adding more and more attributes, what is the maximum number of attributes that X can contain? It's the total number of attributes that you have, right? You don't have an infinite number of attributes. You have a fixed number of attributes. So in the worst case, X will grow as much as the total number of attributes that you have. Right? It can't go beyond that. Right? Because of that, at each iteration you are increasing X by 1 and you have an upper bound, and therefore this algorithm has to converge. It can't go to infinity, right? Because each step you are concretely moving, making progress, and in the worst case you have all of the attributes as an upper bound, and therefore that is when you will definitely stop before that. Okay, in the worst case you will stop at that point. Okay? Okay, so this is why the algorithm converges. So let's work through a simple example. So let's say I wanted to, I have this set of functional dependencies, A, B, C, AB implies C, AD implies E, B implies D, AF implies B, and I want to find the closure of A comma B. So if I were to apply my closure algorithm, how would I go about it? What is the first rule that will help me expand this set X? So I start with X equal AB. Okay? Give me a rule that will help me expand X. Yep. Yep. AB implies C. Yep. So I have AB implies C, A and B are present in X, C is not present in X, so I can change this to AB, comma C. Okay? Good. I made progress. What next? B implies D? Sure. So I can, B, the left hand side is present in X, right hand side is not, so I can change this to A, B, C, D. Okay, what next? AD implies E. Yep, so A and D are both present in X, E is not present in X, so I have A, B, C, D, E. Anything else? No, right? So the only function dependency that I have not touched so far is AF implies B. That I can't apply that because F is not in my set. Okay? So that's it. That's the convergence. So AB plus equals ABCDE. Right? Right. What about AF plus? Okay, so X starts off by being A comma F. Yep. So what would I apply first? AF implies B? Sure. So I would change this to AFB because A and F were in my set X, B was not, so I have AFB. Now I can do a trick, right? I knew that AB plus is equal to A, B, C, D, E, right? Since AB plus, the closure of AB is A, B, C, D, E, I can add that to this set because it would be basically like going through the set of functional dependencies once again. So I would have A, B, C, D, E, F, correct? Do I need to do anything else? No, right? At this point I'm done. I have all of the attributes in the closure and therefore I can't apply anything more. So I have an upper bound to how many things I can add, which is the total number of attributes. Here I have only 6 attributes and therefore I will stop when I hit 6 for sure. Okay? Alright, so we did this. So turns out this algorithm is correct. I'm not going to cover the proof in class. Please take a look at the textbook. There are 2 parts to the proof. The first part is that anything that we determine to be part of the closure deserves to be there. So this is a soundness guarantee. And that there is nothing that we miss out on. This is a completeness guarantee. Okay, so both of these together give us the fact that the overall algorithm for closure is correct. Okay, so I will stop here and then I'll continue in the next class. So I'll talk about the uses of attribute closure in the next class.